I do want to give a thanks right off the bat to all of the state specialists involved in this, bringing in what I think is an amazing, really good group of speakers. We like diversity, so we brought in some really fun out-of-state talks. They're going to be good across this, and so with that, I'm going to welcome our department head, kind of opening ceremonies before we begin our first session. So Dr. Wade Thomason, Plant and Soil Sciences Department Head, will give you your welcome and thank you for coming.
Good morning, everybody. Appreciate the opportunity to address you guys today. Obviously, a very familiar crowd. I'll begin with this by telling you that my daughter believes that the official Aggie uniform, no matter in what country you're in, is a vest of some sort, puffy vest, fleece vest, whatever it is. And so we were at a basketball game earlier in the year, and she pointed and she says, "There's one of your people down there." And I said, "Are you sure?" And he turns around, sure enough, he's wearing an AgriPro cap. And I was like, well, busted it yet again. So I see we're among friends here on that front. I wanted to give you guys just a little bit of an update from the division and from the Department of Plant and Soil Sciences. Anybody that came in from Monroe, from the north end, probably noticed the construction there on New Frontiers Ag Hall. If you didn't, they're moving right along with that. That's going to be the new home for the majority of the departments and individuals that are in Ag Hall currently. Brand new facility, very much student focused. I think I heard somebody say in the past that, the student interaction space in the current Ag Hall was the front steps. And the new version will definitely change that. There's going to be a revision of the dairy bar in that building, as well as a lot of other student-focused areas for them to sit and talk and interact and enjoy the space. So we're really looking forward to that. We're planning to be moved in there in summer of '24. We're scheduling classes in there for next fall, so an exciting time for our faculty, staff, and students. I also wanted to give you a few updates from the department individually. We have the largest undergraduate enrollment this fall that we've had since 2016, so we've grown a little bit, and I think those of you in the industry, especially those that are doing any hiring of our young people, would appreciate the fact that we'll be hopefully training a few more, putting them out in the industry in the coming years. I also wanted to share with you that something that many of you know, but since I've been here a little more than a year, we've done a significant amount of hiring. We hired 3 faculty members in 2023, 2 in weed science and 1 in soil fertility. We have Jeannie Dudek, who will be joining us as our extension cotton specialist here this spring, and I'm excited to announce that we're going to be able to hire 2 more soils-based faculty in 2024, 1 in soil conservation in a role similar to what Jason Warren has been doing, and then another to direct the soil and water forage analytical lab, so Brian can drop his overload and extra one of his mini caps and let someone else take that over. And I know he's fortunate about that, but I know Highland has served the industry in a lot of ways over the years, been a very valuable partner, and so we're looking forward to refilling those positions and continuing to serve the state. So welcome to OSU. Enjoy your time here. If you have any complaints or issues, definitely share them with Brian.
Okay, all right. Okay, with that, we're going to start our first session on irrigation and water dynamics, and Dr. Sumit Sharma is going to be the leader of this session. We'll be introducing our speakers. So with that, Sumit.
Thank you, Dr. Arnold. Welcome, everyone. So this will be the first session about irrigation and water dynamics, and our first speaker for this session will be Dr. Jonathan Aguilar. He's an associate professor at Kansas State University. He's an irrigation engineer and works at Garden City Southwest Research and Extension Center in High Plains, Southwest Kansas, and has done a lot of work in irrigation scheduling and irrigation scheduling tools and strategies. And we welcome him to share his talk with us on irrigation technology.
Good morning, everyone. I'm sorry to start the session. I'm sorry to start the session here, not with an orange, but probably a purple. But I hope that to be able to share something with you about irrigation scheduling, in particular the technology. Just a show of hand here, who has or has irrigated land that they are managing? Okay, so there's quite a few, and I think I'll try to reach out to some of the topic as well as when we go to the soil moisture sensor. Is there really a role of soil moisture sensor in the even in the dryland condition? So that's what I'm going to hope to do today. So again, my name is Jonathan Aguilar. I'm with Kansas State University, and I'm very similar to Sumit Sharma. I'll be the irrigation engineer there. I am based in Garden City, so very west. So we do. So I am located there with most of our irrigated acres in that state. So what I'm going to talk to you today is about water management. So I'll be broad and be and hopefully to be able to help you out in terms of your management. So just a quick overview here. I'll talk about a little bit about the statistics and water management. No, I'm not going to let you make some computation about the statistics, but I'm just going to show to you what are the trends that we are seeing right now. So I see that there's quite a few of you that don't have irrigated land. We thought that it's not going to move east, but we are seeing that it's moving east. And then some soil moisture sensor later on that I'm going to talk about. So this is what I'm talking about. So about 3 years ago, we were in Alabama helping out producers there expand their irrigation system. Why do they need irrigation system when it's raining so much there? So the green dots here, or the green pictures here, are acres that are going into irrigation. The brown or the brown or the red ones are the ones that are losing irrigated land. So there's a movement of irrigated acres out in the east. Why? Well, I'm going to talk to you a little bit about what's going on in that one, because we have seen this even just in our state. And I just saw the Oklahoma here. There's also an increase in irrigated acres in the central portion of the state. So what you probably know better what's going on in this area. But one of the things that I think is going on is that we are having those times that, well, at least in the Alabama, they say that we have those 2 weeks that it doesn't rain. What happened to my crop? It fails. So if I could have an irrigation system at those 2 weeks, just 2 weeks, I just need to use those irrigation system those 2 weeks, I think I'm going to make it through the cropping season. So yes, we are seeing that as we talk more about climate change, more intense rainfall and less frequent rainfall. This is something that people are thinking about. It's the insurance of having those crops go through those 2 weeks without water or without rain to be able to survive. The other thing that many farmers are also looking at this irrigation system is that it stabilizes the yield. Yes, we know that irrigated acres do have a higher yield compared with the rain-fed, shown here by the lines in blue and the red. But also at the back of those graphs, you could see shaded lines, shaded area. What are those? Those are the dry years. So, is irrigated field affected by dry spells or dry years? Yes, the yield goes down. But look at the difference between the magnitude of a dry land and a rain-fed. Just look at the 2012 dry spell there. So the magnitude of the drop in terms of the yield is also significant. So that's the other reason why many producers are also looking at the converting into irrigation, just because of those stability. So I always talk to many producers, say, so if this is your only income, which one do you like? A more stable income or a more erratic income? I think we do agree that it's got to be on the more stable income. So, which points out to why we're talking here about the water management. So, you probably are, many of you are probably in the yielding corn in particular, to about 200, 250, or maybe between 150 to 200. Is that right? In Oklahoma, is that the yield? But I'm not sure if you have also noticed that in 2019 there was the corn contest national, and the winner. How much do you think was the yield for that winner? It was 619 bushels for corn under irrigation. 619. So we are nowhere close to that yield potential of corn. So one of the characteristics of that winner was that it was in irrigated field. It was tilled and it was mulch. I think it was there was mulching. It was using a seed, a pioneer seed, and there was ample nutrient that are going on. So what I'm saying here in the yield gap is that we do have a potential to be able to increase yield without expanding our acreage in terms of the area that we are planting. But it has to go through, once that seed gets into the ground, it has to go through a lot of challenges, from the weather to the insect and pest, nutrients, the seeding, whether you plant it shallow or deep, the weeds also, and most importantly, the water management. So those are the things that we will be talking about, and focus more on the water management. And if there's any way that we could probably reduce this yield gap, I think we will be in a better shape in moving forward and helping out. So in terms of irrigation management, there's going to be a lot of things that we could possibly talk about. System efficiency, application efficiency, planning tools, scheduling strategies. I will not go through all of them, and I think Sumit will be talking here very shortly, but he will be also talking one of this aspect. But I will be focusing more on scheduling. But before we could even talk about scheduling, let's consider some of the options that are available for us. So we think that in order to be able for us to use that water for irrigation or for application or for supplemental application of that water for those 2 weeks, I think it's important that we should be able to look at the efficiency of that system. Not everybody have a 1,000 gallon per minute well. So we probably are looking at the possibility of putting that water more efficiently into the ground. It's good for the bank, it's good for our pocket, and it's good for Mother Nature to be able to just apply the right amount with most efficient system. And there's several of them. And I think the most efficient so far that we have in our toolbox for irrigation systems is probably the drip irrigation, which could reach about 95%. So even I've seen numbers that it could even reach about 98%. So for almost every gallon of water that you put it, 98% of that water is going to be used by the crop. So take note of that, used by the crop. So I'll get back again later on that aspect. So as I mentioned, this is our Cadillac for irrigation engineers. This is a subsurface drip irrigation. It gets the nutrients and the water, nitrogen in particular, and the water right where the root zone is. So able to minimize any loss if possible. But if you could not afford, the problem with SDI is that it's relatively expensive. So if you could not afford it, the center pivot is probably another option, and there are several options that are relatively efficient as well, closing to about 85% efficient, from LIPA, LISA, MISA. We've got all of the acronyms that we could possibly use. So the LIPA is low energy precision spray, mostly used. I think many of these are in the Texas Panhandle area. LISA is probably what you would see about in any places, and MISA is also one of those that are being used as well. So there's a lot of ways that you could apply those water and in more efficiently. But again, from the engineering point of view, we would like to get up to 100%. Our colleagues in Nebraska are saying that they could reach more than 100%, because in the humid east, where there's humidity. Once that water gets in, apparently it adds a little bit more of water or condenses that water. So, but anyway, from the engineering point of view, we would like to reach as much as possible the 100% efficiency. We've been dealing with one of the devices there. The mobile drip is probably the newest item that we put into this chart, which we think is very similar to a LIPA. That's why we put it at relatively high efficiency as well. So again, going back to this efficiency, why focus on efficiency? Because if you have a well that is not able to pump out the amount of water that you would like, so what you could possibly do now is trying to increase your efficiency and still get a good irrigated acres. So for example, you've got a 128-acre center pivot. If you've got a 60% efficiency, if you've got about 70% efficient system, you need 857 gallons per minute. But if you bump that, efficiency to close to about 90%, then you could lower down your gallons per minute or your rate to about 670 in terms of the application rate. So that's how important the efficiency is in terms of the use of water. So, been talking about efficiency. So is the irrigation efficiency a fixed value? It is affected by, no, it is not. It is affected by a number of factors, and I will show here in a minute, because there's a lot of what we call losses that you could get into a system. So the air loss, which could be either a drift or a droplet evaporation. Canopy loss, could be a canopy evaporation or foliage interception. Surface losses could be soil evaporation, runoff, or even just the water, soil water evaporation itself. And deep losses, which is called the deep percolation. So there's a lot of losses that we could possibly consider. In Texas, they did a study as to try to figure out really what are those losses and how much are those losses in terms of their system. So they were able to parse out the water that is being applied on the field. So try to find out which part is being used for transpiration, which part is lost through droplet, through canopy, and through soil. So even if you're rain-fed, you are going to lose water through transpiration and soil evaporation. So that's basically the last bar over here is that it's going to, you're going to lose them whatever. But if you are going to irrigate, you're also going to incur losses due to canopy and also due to droplet evaporation. So combined, and also you will increase your soil evaporation just because you are also wetting that soil. So you are also going to lose a little bit more compared with the dryland. So combined, it's roughly about 0.15 to 0.17 of an inch for every inch that they apply. So you could also look at it as 15% or 17% of it is lost every time you apply that water. So going back to that idea of thus the efficiency changes. So if you don't have runoff, you still have the losses that I mentioned. So 1,700 or 1,700 of an inch is lost for every inch that you apply. So at the end, you might have about 83% efficient system. So that's without any loss. Well, if you have runoff, if you have moving water in your field, and it's probably about 1/10 of an inch, you immediately lost your efficiency by 10%. So 73%, from 83 to 73%. Now you'll say that during in the middle of the summer, you say, oh, it's going to be hot, so I have to catch up and just go round and round and try to apply water as fast as I could. Well, if you're putting in 7,500 of an inch or quarter of an inch, 3/4 of an inch for every pass, you are actually losing your efficiency. Because every time you pass, you are going to lose that 1,700 of an inch. So you are going to lose that whatever. However, if you are going to be slow and deep in terms of application, and I think this is what Dr. Sumit Sharma is going to talk later on, you are actually going to increase your efficiency over time. So other way to look at it is if you are a consultant or if you are fixing something, every time you visit, you're going to charge them a service fee. So if I do a lot of visit on a person on a field, I'm going to charge a service fee, and that's the same for irrigation. So every irrigation event, you are going to lose that. I call it a service losses or service fee, 1,700 of an inch every irrigation event. So if you would like it to be fast during the summer, go ahead and make it fast. You're going to lose a lot more in terms of that compared when you are pushing it to you're pushing your water down as deep as possible. So which points back to, does it matter if we put water on the soil, on the plant? Does it have any effect on that matter? Is it really a loss? Well, actually it's not a loss. A portion of it is actually being used by the crop. So do you know what the condition of a crop is in the middle of the summer during the growing season is? They like it hot in the field. And that's how they produce the crop. They produce yield. They want it hot. So what do they use for the water for? 95% of that water is being used for cooling. Almost 95% of that water is being used for cooling. So if you are in the field and it's very hot, and you've got a glass of water, a bottle of water, what do you do to cool yourself? Well, there's two ways. You could pour that water on yourself or drink it. Which one will last longer? Drinking that water. Well, basically that's what this graph shows. That as that water is being applied in the field, as long as the soil is wet, transpiration is moving, is working. So that's the line over here. That's transpiration. So transpiration is working on the plant. But once that droplets gets into those leaves, the crops immediately say, okay, I don't need transpiration to cool myself. I'll use the evaporative cooling of that on the leaves to change myself to this mode. So it changes itself. So this is the canopy evaporation. So the cooling effect of the evaporation on the canopy changes immediately. Once that center pivot goes through, it's now dry again, and then the leaves are dry. What does the plant do? They change back to transpiration. So that's what I say is that all of that canopy is actually lost, but it's just short-lived. It is still being used for cooling, but it's very short-lived. So that's what this graph actually means. So it's basically similar to us. If we pour this water on us, it's going to have cooling effect, but it's short-lived. Once my shirt is dry, the cooling effect is gone. But if I drink it, probably I could last more than just an hour of a cooling effect. So I'm still being able to be hydrated. So again, going back to those general categories. So we talked about system efficiency and application efficiency, and I'll be dealing more with scheduling here. So one caveat here. In terms of irrigation management, binoculars is not an irrigation technology. Nope, it is not. I just want to clarify that one. Because I do have proof that some people think it is. So here, in the US, so they did a survey, and guess what? 7% of the people think that if their neighbor irrigate, I have to irrigate. And I think that's probably true also with your yard. If my neighbor irrigates, I need to irrigate too. If there's water on my neighbor, I probably have one of the farmers that I was talking to said, sometimes it's the blinking of the light during the night. If that center pivot is blinking, it's like something that tells me that I also have to start my system. So it is. So it is true that it is. Some neighbors are actually looking on their neighbors to be able to irrigate. It's not the best way to do it. Well, good if your neighbor is doing something on his farm that is probably more scientific or more likely. But your field is not the same as his. So that's one thing. I look at across all of the other states, irrigated states, there are several that are also doing it. I would say that Kansas at one point, there's about 15% of farmers were looking at their neighbor. I'm glad to say that now we were able to lower it down. I look at Oklahoma, there's still 4 out of 100 farmers that are looking at their neighbors to make those decisions. So we still have a lot of work to do. So Sumit and I still have a lot of work to do to be able to convince that, no, your neighbor is not your irrigation schedule. You could use a soil moisture sensor, a plant-based sensor, and ET for that matter to be able to make that decision, because not all of the fields are the same. So with that, so let's try to identify what's really irrigation scheduling. So I highlighted here that it is a part of management focusing primarily on when and how much water is applied. You see, there's a part there that there's a management. So even though you have a soil moisture sensor, doesn't mean that you are already doing a scheduling. There's a management part of it. And then even if you have an irrigation system, doesn't mean that you are managing it well, because there's a management part of it. So how do we really define irrigation scheduling? So it's a process of determining when to irrigate and how much should be applied. This is probably a textbook definition for irrigation scheduling. And there's several of us in the think tank that in the High Plains that think that this is probably not the best irrigation scheduling definition that we should be probably using here, particularly in areas where it rains. Does it rain in Oklahoma? Yes, it does rain. It also rains in Kansas. And so here's the definition that some of the irrigation engineers are actually pushing. It is the process of delaying any unnecessary irrigation with the hope that the cropping season will end before the next irrigation is needed. So let's pause for a while and look at this definition. This looks like a rain-fed irrigation, rain-fed field, without relying on irrigation. If we don't have those long periods of dry spells or dry days, so you don't really need irrigation if you don't need to. The other part of it is that you are relying on free water from Mother Nature. So if you could delay in such a way that you could wait for the Mother Nature to deliver the water, then you're well and good. You're not going to leach any nutrients, and you're in better shape overall. So why? Because there's also a lot of impact that you could possibly get. So it reduces your pumping cost. It increases your net returns if you don't need to irrigate. It could save you in input cost. There's a study in Nebraska that tried to document how much water is lost due to I forgot the nitrification. It could be as much as 20% of the input cost. So that's almost about 11. Or probably it is outdated in terms of the price. The price is probably almost doubled by now. And also, where areas there is a limitation in terms of the water, of course, you could use that water for future use later on. So I mentioned a while ago that there's better ways of doing irrigation scheduling, and we could probably lump them all together into 3 categories. It's either a weather-based, a soil-based, or a plant-based. Which one is better? I'll talk more about that. But if you are going to use one of them, that's good. Do not use your neighbor. You see, neighbor is not here. So neighbor is not part of your irrigation scheduling, okay? So if you are going to use one of them, that's good. If you use 2 of them, that's better. And probably the best, if you have access to all 3 of them, that's even better. That's even the best option that you could possibly have. So what are those irrigation scheduling tools that we call the weather-based? We based it on the ET, or evapotranspiration. So most of the universities have some kind of irrigation scheduling tools that we call. In Kansas, we call it CanSched. Not necessarily because it is from Kansas. We call it because you can schedule. You can CanSched. So in Texas, they do have the DM, WISE. They do have the Colorado. They do have the WISE. Right now, NOAA is trying to assemble the FRET, I forgot the name of it, but the ET there is evapotranspiration. So there is a collective effort from the universities to be able to support you with this type of system. If you don't know, you could use an ET gauge or an atmometer in your field. And we tried to test our mesonet data with the ET gauge. And for a while, I was told by my predecessor said that they were asking producers to go out and read the ET atmometer and then try to also tell them what the mesonet number is. And at some point, the farmer was saying, why do I have to go out and read your atmometer when it's almost the same as what I'm reading in my mesonet? So there is a good correlation there right now. Soil-based, and I think this is where many of the industry are focusing more, is trying to figure out the soil moistures using the sensors. And I'll talk a little bit about the sensors later on, but there's several of them that you could possibly use in terms of the soil-based. Gravimetric is still one of them as part of the ways to be able to figure out if you have water or not in the field. Neutron probe, hand probe, electric resistance, and electromagnetic part, and I'll try to talk a little bit more of that. Many of the technologies right now are also focusing on infrared or the plant-based. So as I mentioned a while ago, the crop uses about 95% of water to cooling. So what if there's no water available for them? What does it do to the crop? It heats it up. That's why the thermal imagery are actually the most important for irrigation management, because it shows up immediately. So if they could not cool themselves, the plant the temperature will rise within those canopies. So that's the reason why we look at the thermal camera to be able to detect any stress on the crop. Dendrometer, there's some of those, osmotic water potential, NDVI. There's a lot of work that is being done, and just visual. And I think this is probably one of those that the farmers are doing is, yeah, sometimes if it is already wilting or it is already brown in the field, sometimes it's too late in some cases. So that's why in the research we are trying to see if there's a way that we could, before it gets too late, is there another way that we could detect the crop for telling us that it is already getting dry. So again, irrigation scheduling starts by knowing what you have to manage. And many times you have to look at the soil, you have to look at the plant. And I'm going to just go through here roughly what we are talking about. So in the field, in the research, our gold standard for measuring the soil is the weighing lysimeters. Basically, we take a chunk of soil and try to figure out how much water is being added and how much water is being lost by having a weighing scale at the bottom of it. So that's a lysimeter. So we try to get as much as possible all of the materials. If we don't have the weighing lysimeter, a good way of doing it also is the gravimetric. Again, trying to weigh what is a wet soil, then dry it up on the oven, and figure out how much is lost. That is the water itself. So those are typically the direct way of measuring it. Sometimes we do a water balance wherein we try to figure out as much as possible what is going in, what is going out, and try to figure out what's left in the soil. Transpiration, evaporation, runoff, and deep percolation are what we call withdrawal from the soil column. And then rain, irrigation, and even if you are in an area where there is a seepage, you could also consider that as an inflow for that field. So those are the water balance. And it's almost very similar to your bank account. You've got deposit, you've got withdrawal, And before your banker call you, hey, you've got a negative here, at least you will know where you are in terms of your management. And this is a snapshot of what the CANSCAD is look like. So basically, you have deposit and withdrawals, and it will try to calculate how much is left in your field. And you could access this in this website. So in reality, when you are also in the field, what are the ways of measuring the soil but in practicality? So some of you might be crop consultant here, and the way that you do it is you probe the field, and that's actually a good way to also figure out what's the soil moisture in the field. But in science, we categorize them either direct or indirect. Unfortunately, indirect, there's a lot of them that are measuring the water using surrogate properties. And I'll tell you a little bit more about that later on. So there has been a lot of excitement about soil moisture sensor. Well, I think it is right that we should be excited about it, because we don't need to be in the field anymore to figure out if it is dry or wet in our field because of the soil moisture sensors, because they do have also already telemetry. If you have a phone, then you're good to go to be able to figure out what's in the soil or what's the moisture in the field. Response time is impressive. Compared with the gravimetric, you have to spend about 48 hours to figure out, oh, I'm dry, or I am still wet. So the response time is impressive. The graphic interface, even those that are using eyeglasses could probably read them now. Electronics is impressive also. But most of the issues are still there. Accuracy, installation. Anybody here that is working on real estate? Their motto is location, location, location. So if your sensor is not at the right place in terms of the depth, in terms of the field, in terms of the representative soil, then you are not really getting a good numbers on those. And also the calibration. So there are sensors that really need calibration, and I'll talk a little bit more about that. Part of it is because we are only talking a very small amount of soil sample. Roughly, I typically have, I forgot my tennis ball. It's roughly the size of a tennis ball. So think about it. If you are an irrigated acres of a center pivot, you're going to make a management decision out of that tennis ball volume. So if that is not a representative field or soil, then you are actually getting a wrong feedback on the field. So it has to be very good. So to illustrate what I'm talking about, the soil moisture sensor regarding the surrogate, so what do you call a device that measures temperature? So it's thermometer. A vehicle speed, speedometer. A rotation, it's tachometer. Color, we call it a colorimeter. Voltage, voltmeter. Soil water content, moisture sensor. So what happened there? There was no water that is being measured by the soil moisture sensor. So it's because it's using a gravimetric, it's using indirect sources, and it could be anything that is related to water. So I'm going to just mention just a few. It could be the tensiometer. So the tension between the soil water potential. It could be the neutron count, and that's what we are using as a gold standard. Neutron count, it's looking for the hydrogen molecules. So we are assuming there's no other hydrogen molecules in the field rather than for the water, so we use the neutron probe. Electrical resistance. No wonder if you are not allowed to hold on to any wires if you are wet. Basically, that's the same parameter. If electrical resistance differs between a dry and a wet item. Capacitance, it's almost like a TV. If you have an antenna, it tries to emit that signal and tries to figure out, okay, if it is wet, it has a different signal. If it is dry, it has a different signal. And I will show you some numbers later on. Constant frequency, there's also the frequency type and transmission time. So again, all of these are electronic in one way or another. The advantages of each have also, each type has also advantages and disadvantages. Electrical resistance typically are relatively cheaper, but it could not accurately estimate, particularly if it has some salt in it. So that also messes up those measurements. So this is where most of the soil moisture sensors are relying from. The property of the soil or the property of each of the materials within the soil. So you could see if it is air, it will measure 1. If it is liquid water, it measures 80. So this is actually a very good way to parse out what is in the soil. If it is organic matter, ice, clay, they're all within that less than 5 matters. So another thing why we mention about installation is important in the soil moisture sensor is basically these numbers as well. Look at the number of air and the number of water. So if there's gap in the soil moisture sensor, what happens to that number? It's either 80 or once it dries up, it becomes 1. There's no in between. So that's where we say that it is really important that that installation is crucial, because you could either just get air or water, or if there's a gap in between. So that's where it is very crucial. So if your installation is faulty, then you most likely you will get a faulty numbers just because of these properties. Looking at some of the other system, antenna would be another way of looking at it. Here's a summary of what the ARS is saying in terms of some of the soil moisture sensor. If you don't calibrate them, and if you have clay on your field, if you are using a capacitance type of system, forget about it. But there is a value in this, because maybe you could just try to calibrate it. Again, this is on the, if you don't calibrate your system, then most likely you will have a very faulty numbers that you are going to get. So with collaboration with OSU and K-State and Texas, we came up with some of these tips. We know that there's a lot of things that could happen on a soil moisture sensor, so we tried to help you out. There's actually an extension bulletin that is published by OSU, and we try to help you out, try to figure out which one is going to be useful for you. Again, one of those, the first thing, location, location, location. So we joined the motto of the real estate people that it's very important to look at that. If you are more of a person that looks at the video, we also have some video for you. About 4 years ago now, we tried to invite all of the local dealers of soil moisture sensors in the area. We've got about 10 of them, and we did a video of help them out, tried to install them in the field, and we tried to, OSU in particular, help out in trying to come up with this video. And so it's still on the web, it's still in YouTube, hopefully. Put a like on it, subscribe on it, something like that. No, we're not. But this is something that that could help you out. Mention about the soil sensors, plant sensors. There's still a lot of things that are going on. As I mentioned, it's important to be able to look at it from the thermal point of view. Right now, I would say that the thermal images are more troubleshooting management tool rather than a day-to-day management tool yet. So we still have a lot of things to sort out in terms of the research, but it is actually an important tool for us. We could get it from the satellite, or we could get it from the airborne thermal images, which is a more frequent flight, if you may. So the satellite could be about every 2 weeks. Airborne could be every week, depending on your subscription. If you like more frequent, we could also use the UAV for some cases. You could do it almost every day or every other day in terms of the management. Or you could have it on a ground-based, wherein it's looking at one field every time and trying to manage, okay, it is already getting low, or the water is getting low, so it is getting dry. So that's another way. Of course, you say that, oh, it's only looking at one portion. So there's a lot of, there was a study that, how about we put it on a center pivot? It could look around the whole field. Well, yes, it could look around the whole field during the whole day, but the whole day could also mean during the nighttime. So what does it see during the nighttime? So they have to almost calibrate it such that you have the models to fill in those gaps. Or during the dawn and the dusk, there's a big difference between the thermal differences between those crops in the dawn or the dusk or even the nighttime, compared when it is right in the middle of the day. So they're trying to fine-tune this technology, and hopefully it will be useful for many of us. So one of the take-home messages that I'll mention is that, yes, going back to that idea that if you are in an area where it rains, there's several tools that you could use, either the ET-based or the plant-based or the soil-based, to be able to figure out if you have to wait or you have to irrigate. So if we could get those timely rainfall, good. If not, then we have to irrigate to maximize the yield for our crop, or even just to make it get through to that season. Because that's one of the things that we have heard from Alabama is that, well, I planted, there's a lot of water when I planted it, but after a month, Mother Nature shuts off his system and it's dry. So after being dry for 3 weeks, it rained again. But at that time, it's too late for the crops. So if we are able to fill in those gaps, then at least we have something to harvest at the end of the season. Another way of looking at it, if you are driving, maybe you could use these tools as your fuel gauge. How far am I to the next pumping station or gas station? If I could get it through to that gas station where it's relatively cheap, then I'll try to make it go to the effort of almost getting it to the empty before going to the next gas station. So it's relatively cheap to go to that gas station rather than fill it up here, where it's probably about $50 higher in terms of the price. So which is more like a pumping. So with that, thank you very much for your attention. Hopefully I get something for you to be able to figure out. Going back again to my idea, to my thought that this could also be useful. I've heard people say that soil moisture sensors are also useful for dryland or for dryland fields. Why? Because at least they know what type of crop they're going to plant the next season. If it is dry, then these are my options. If my profile is wet, these are my options. So there is also a use for you for using those soil moisture sensor. So with that, I used up most of the time, or I'm open for any question.
We have time for one question. That soil sensing method in that survey, did that include yield method or what was it?
Yeah, there was also a field method in that survey, and I did not grab that because that survey also says when they conducted the survey, they did not specify as A, B, C, or D only. They actually say you could fill in as much as possible. So there's a possibility that one is using plant-based as well as probably a field method. So that's why I did not pick it up. But there's still some people that are using that one way or another.
Thank you so much, Jonathan.
Okay, thank you very much.
All right, our next speaker is Dr. Joseph Burke. He comes here from Texas A&M University. He works as, he recently joined, I think this year, as assistant professor in irrigated cropping systems, and is working with cotton, wheat, and I think peanuts as well, and sorghum. He's working with many crops. So he is going to be sharing his presentation on soil water dynamics following cover crops and semi-arid production systems. So with that, I'll welcome Joseph.
We'll go with this. So I apologize for that, everyone. Good morning. Yeah, I'm a bit of a pacer, so I will try and stay here behind the lectern. But good morning. I want to thank everyone for being here today. Drove up from Lubbock yesterday, and it was nice. I had a field day up in Perryton, early in the summer, and it was nice to see a little bit of crop that was actually getting harvested on my way over here from Lubbock yesterday. So I did my undergrad at Texas Tech University, and I was thinking about the last time I was in Stillwater, and unfortunately that was in 2009 when we thought we had a good chance of knocking off OSU from being in the top 25, and you defeated us in like the last 3 minutes of the game. So that was the last time I was here, but it's nice to be back here in Oklahoma. So, like Sumit said, recently started. I'm about 7 months into my tenure as a new faculty member at the Texas A&M AgriLife Research and Extension Center based in Lubbock, Texas. I'm going to share some information today about some of our cropping systems that we have there on the High Plains. How many cotton producers do we have in the room, or anyone that works with cotton? All right. Well, for the rest of you, you're going to get an education in cotton today, because when we are in Lubbock, that is the crop that we work with, right? Lubbock and the 8 counties that touch Lubbock produce about between 40 and 60% of the U.S. cotton crop every year. So naturally, as a researcher in that region, most of the stuff that I do is in cotton. But when I was hired on, one of the things that was a big push for the state was to have a researcher that focuses on sustainability of row crops. And like any good researcher, I came up with my own definition for what my program was going to be focused on, and that's regenerative agriculture on the High Plains. And that's just the current buzzword. But we define that as the continued capacity of agricultural systems to function in a changing climate that supports soil health, communities, economic output, environmental sustainability, and the resilience of those systems to outside threats. So one of the key words that I want to talk about here is sustainability. The primary goal behind anything that's sustainable is understanding what you're trying to sustain. And for me in my program, based on the stakeholders that I have in Lubbock, I focus on sustaining agricultural production in the region, and that really focuses on our economic output. So this is a map of Texas on the left-hand side. And it's going to be weighted by county size based on agricultural outputs. And as you can see, the High Plains of Texas is really where most of our agricultural production in the state comes from. And every year it's about $13.5 billion in the 27 counties in the northern High Plains, okay? And so that's a huge economic output for us. We need to be able to find a way of sustaining that, but it's becoming more and more challenging as we work with limited water resources from the Ogallala Aquifer. So where we are in Lubbock here, we are withdrawing the aquifer at the greatest rates of anyone else in the Ogallala Aquifer region. And for us, it's about trying to maximize our sustainability while sustaining our crop production throughout time. One of the interesting things to note is every year the High Plains Water District, which is our main water cooperator in our area, publishes a map of capped wells. And you can track from year to year, it's about 10 miles a year, starting in Stanton, which is about right here, moving forward where they cap the well line. And so they go from green to red. And that's essentially, when they cap them, that's about 9 meters of saturated thickness, and there's no more water that you can withdraw from the aquifer at an economic rate. And so for us, that is our risk area. In Lubbock, that means that we have about 50 to 60 years of water remaining before we are expected to run out of irrigation resources in the Lubbock area. And so this is what we're thinking about. This is what my producers are concerned about. And so I'm going to bring some of those insights that we have for you today. And what makes it a challenge for us, and like I'm sure many of you experience here in Oklahoma, we just have a demanding climate that makes it a challenge for us to produce crops in our region. So our average temperature is anywhere between 55 and 63 degrees Fahrenheit. Now I will say that that's the average annual temperature. We can get anywhere between 75 and 100 degrees starting in May. And this year we had, 36 days of over 102 degree temperatures, right? In La Mesa, Texas, where I conduct most of my work, which is about an hour south of Lubbock. Our average wind speed, 12.13 or 12.3 miles per hour. We're the fourth windiest place in North America in Lubbock. So you add that with our limited precipitation and just our volatile climate. Since 1980, our average precipitation has actually dropped from 16 inches to about 14 inches, but I'm leaving this up with our 30-year average that we have here. And so what I show here is this is across time in La Mesa, Texas. So we're looking at our precipitation, wind speed, and then our temperature. And what you can notice is that our lowest months for precipitation is also our highest months for our wind speed, which tends to lead to quite a bit of dust storms in our area still. And so I'll talk a little bit more about that tomorrow and why we implement cover crops in our region. But just note that this is going to be a pretty harsh climate for us to try to get a cotton crop into. And what's also important to note is this figure over here on the right. This shows our precipitation relative to our evapotranspiration potential in Lubbock, Texas, where we can evaporate 2 to 3 times as much precipitation as we can get in an average year. And so it's going to be hot, it's going to be dry, it's going to be windy. How do we balance crop production in this region? Now, when I write proposals for federal grants, the number one comment I get back from reviewers that aren't from this region is, why don't you just abandon crop production entirely, right? If it's so hard and you're drawing down all the water resources, why don't you just give up and move all those people somewhere else? And my question would be, well, what do we do with over 1 million people that live in West Texas that depend on agricultural production? Not only with row crops, but also cattle and dairies. All of these things we have to balance. And so we have to find ways to maximize our resources. And what makes it even more of a challenge is just when you work with cotton monocultures, there's not a lot of time to implement anything other than cotton. So we will plant cotton anywhere between mid-May and June, sometimes July, depending if we get hailed out, and based on what our crop adjusters say. And then we're going to harvest that cotton crop anywhere between October and December. For our organic producers, they're actually harvesting in January or February because we're waiting on those hard freezes to defoliate the cotton crop for us. And then that leaves us a very limited time to implement any kind of conservation practice like cover crops and get that cover crop established into our systems. And so one of the things that we can try to do to try to capture and store this moisture is we have to focus on practices that are perceived to reduce the capacity of soils to capture rainfall or stored soil moisture because those will hinder adoption in our region. How many of you have producers or are a producer that don't think that cover crops can work for you because of water? Right? That is the number one thing. I go to meetings and I talk about how cover crops can enhance water storage capacity, and you can see the producers looking for tomatoes to throw, right? Because they're like, there's no way, if I get 9 inches of rainfall in my cotton growing season and my cover crop uses 4 inches of water to grow, that math doesn't make sense, right? Because we only have another 3 inches or so of precipitation during those winter months that we can rely on. But I'm hoping to show you some data today that I'm hoping may convince you, at least in La Mesa. All right? And so what we're really focusing on is how do we retain precipitation and maximize its water storage capacity inside of our soils. Okay? So we have this long-term system in La Mesa. When I was 8 years old, sitting in Miss Palmero's second grade class, Wayne Keeling, how many of you know Wayne? Agronomist in Lubbock that I replaced in his position. Wayne set up this long-term cropping system that evaluated continuous cotton systems, either a conventional tillage with a winter fallow or a no tillage with a rye cover. Okay, so he established that in 1998. Fast forward to 2014, Dr. Katie Lewis, the soil fertilist in Lubbock, she came up with a new system where they split those rye plots in half and put a mixed species cover in those. And that mixed species included rye at 50%, Austrian winter pea at 33%, 10% hairy vetch, and 7% radish. Now, here's a poll for the audience. What percentage of the mixed species cover that wasn't rye do you think came up and was in the final biomass total? Throw out a number at me. Say that again? 2%, that's a great guess. It was actually less than that. So on average, when we terminated our mixed species cover, we got 99.8% rye in that 50% planting. So what I refer to these now moving forward, and this is one of my many jokes that I'll tell today, I had a rye cover crop and a very expensive rye cover crop that we implemented into these systems, okay? And so just note that this is essentially a seeding rate study because we didn't get any of those mixed species covers to actually come up in the system. And then we also compared that back to a native system. I should note that this mixed species cover was the NRCS recommendation at the time. Since then, NRCS has abandoned that recommendation for the Southern High Plains. So the NRCS does listen to us. They've also dropped their seeding rate from 40 to 30 pounds based on this same study in Louisa. And I will say these are 16 rows wide, and they're about 200 to 275 feet long, depending on where you are in the curve. All right, so despite the fact that we have these really harsh conditions, it's really hard to grow a cover crop, we can actually produce quite a bit of biomass in the system. So figure on the left is looking from 2015 to 2022, the average amount of biomass that we were able to generate in the system. Now, we had wet years, we had dry years, and we had really frickin' dry years, right? So 2021 and 2022, two of the driest years that we've recorded since the 1950s droughts, and what we see is very little biomass was generated. But in certain years, we can get almost 5,000 pounds of biomass in these systems. And that's a lot of biomass. However, that does result in some yield losses. Okay, so this is looking at cotton lint yield across the same amount of time, except we added 2023 in here. I don't know what I was doing in 2022, but I apparently didn't collect biomass in the systems in 2023. So we're just going to ignore that. But this is the cotton lint yield for these systems. And what I want you to note is not necessarily just the yields themselves, but this figure here. So this is looking at stability analysis. So if you take a step back, breeders, especially wheat breeders, came up with this really good statistical system where they said, I grow this same wheat variety across 30 locations. How can I compare that across time and space? And so what they came up with is this analysis called stability analysis that takes the yield of that variety in that specific year at a specific place and averages it within its own variability. So essentially normalizes it to its growing conditions only. And so what we do is we take that same idea and apply it over time. And so anything greater than this black line, or a slope greater than 1, is going to be considered stable. Anything under the 1-to-1 line is going to be considered unstable. And so what we see here is that our conventionally tilled system is our only stable system within this cropping system itself, right? So what does that mean? Essentially what the takeaway message from this is that we get more consistent results with our conventional tilled system than we do with our no-till systems. And why do you think that is? There's two primary ones. We already talked about the first one, water, right? And so tomorrow we'll talk about the other one, which is nutrient dynamics. And so the key here is that what is going on, what is driving the yield loss in our no-till systems? And most people think it's water, all right? And so not here to dissuade you, but I'm just here to show you what our results are for Lamesa, Texas. So this is looking at soil water from November of 2017 until March of 2021. So 3 growing seasons. And what we can see is there's 3 distinct points in time where our cover crop, which is in the colored lines, had limited soil moisture relative to our conventional plots, which is the gray line. And so in 2017, 2018, that's right here. In 2018, 2019, which is a pretty dry winter, we can see it's even more extreme. And then the same in 2019 and 2020. But note where the maroon arrows are, that's where we terminated our cover crop. And by the time we planted our cotton crop, which is the green arrows, we saw a significant increase in the amount of stored soil moisture. Now, all the plots received the same amount of precipitation. They received the same amount of irrigation. The only difference was the implementation of a cover crop or not. And this is looking at years 18 through 22 of the study, okay? Now, I had a producer a few weeks ago who asked me, well, how much more water are you storing in these no-till systems compared to your conventionally tilled systems? And it's not really that easy to do the math, but essentially, if we take a step back and we think about the math itself, we've doubled our organic matter in our no-till systems relative to our conventionally tilled systems, from 0.3 to 0.6%. Now, that may not sound impressive to people from the I states, but for us, that's a huge number. And it comes out to about 70,000 gallons of water per acre we're able to store in these systems. What that producer asked me, though, is, okay, so you stored all this extra water, have you actually captured any more water, right? And so the analogy I like to use is you go to Starbucks and you get a grande, and with our organic matter increases, we now have the venti cup in our no-till system. But essentially, all I'm doing is I'm pouring my grande cup into my venti cup because I haven't created any more precipitation. I've just created the capacity to store more of that active participation or precipitation that we're getting. Okay. However, as you noted, this didn't translate to yield increases, right? So we're increasing our water in our system, but we're not increasing our yield. And I'll talk about that tomorrow. And so what I want to do now is, this is the same figure, okay? But we measured our soil moisture using a neutron probe, so we can count the amount of hydrogens, which is primarily water, in our soils at depth. All right? And so what I did is, imagine you're looking at the soil profile. I've dug a trench, and we can watch throughout time how that soil moisture is changing. And that's what this figure is showing. So we have soil depth here on the x-axis. On the y-axis, we have time. The more red something is, the drier it is. The more blue something is, the more wet it is. And so what we're seeing is that there are distinct points in time right before we terminate our cover crop that we are depleting profile soil moisture. However, if we can terminate at the right time, and this is the key, if we can get precipitation at the right time, which in Lubbock is actually pretty predictable, late May rains are almost always going to happen for us, then we can refill that profile relative to our conventionally tilled systems. And then we have more soil water throughout the growing season relative to those conventionally tilled systems. So there's more water in our no-till systems, but we're not translating that to yield, right? And so this is a long-term study, and one of the problems with long-term studies is treatments change, right? Producers change their seeding rates, they may change the different crops they have. So we decided to change the system itself, and we looked not only at soil, water, and cotton systems, but also in rotation with a wheat cover crop, or a wheat crop itself. And so we moved just across the turn row, and we have these 3 large plots. Each one is about 60 acres. And we are looking at continuous cotton winter fallow system, number 1. Number 2 is a continuous cotton rye cover crop with no tillage, similar to the last system we just looked at, followed by a cotton wheat fallow with cotton in the even years. And to make sure that we always had something to harvest, we also had a cotton wheat fallow in the opposite rotation, to where the cotton was in the odd years, wheat was in the even years. So we always had a cotton harvest in that rotation. And we had 2 irrigation levels in the system. We have a 60% ET replacement. That comes out to about 6 inches of irrigation a year in our system. And we have what we call a improved dryland. We haven't patented that term yet, but essentially what it is we irrigate it just enough to get the crop established, and then it doesn't get any more precipitation throughout the rest of the year. So it's a modified dryland system. And what we can see is very similar to the last slides that we were looking at, where in this cotton wheat fallow rotation, we have, so this is where we had just finished harvesting that wheat crop, and we saw a significant increase in the water storage capacity in the off season with the wheat fallow, which makes sense. However, with our no-till systems, we actually see that in no-till or with the wheat fallow, we actually see a significant increase in our water storage capacity compared back to the conventionally tilled system. And then if we focus just on the cotton growing time itself, we see this here where both at cover termination and at cotton planting, there was significantly more water in both the cotton wheat fallow and the conventional relative to that cover crop system. So how did that translate? Sorry. One more slide, and then we'll get to that. So this is looking at it again across time at depth, and what we see here is that there's much greater soil moisture following that wheat fallow period, which is pretty self-explanatory. And then also it retains that moisture better throughout the growing season compared back to our no-till system or our conventionally tilled system. All right, so how did yields pan out? The last 2 years have been really rough in West Texas for cotton production, and probably here in Oklahoma as well. These yields are not what we would expect to see. We normally expect to see double these yields than we were seeing in these systems. But what we see is obviously with irrigation, we significantly increase our cotton lint yields. And also where we have that cotton wheat fallow rotation, we also significantly increase our cotton lint yields in those systems. All right. So then the other idea, besides just looking at systems, is producers are wondering when should they terminate their cover crops. Now, NRCS in our region dictates a lot of that because to get EQIP funding for your cotton, you have to plant, or you have to terminate your cover 8 weeks prior to the ideal planting date, which in Lamesa, Texas is about May 15th. And so that would normally mean that we're going to terminate in mid-March. But we wanted, because we're researchers, to drag out the risk associated with those systems. And so we planned a study where we're terminating not only at 8 weeks, but 6 weeks, 4 weeks, and 2 weeks. Because we have a few progressive producers that are coming to meetings and telling us that they're planting into green cover, that they terminate same day, and they're not seeing a yield reduction in those systems. Now, as a soil physicist and a water conservationist, I would not recommend that for most of our producers in the region. That's a really high-risk system, and also you can't get the benefit of EQIP funding to help supplement any loss in yield that you might see with that. So these are the dates that we terminated this system this year. This is the first year of these results. And I don't have cotton lint yield, but I have estimated seed lint that I'll share with you today. And so this study, we have a really ambitious Ph.D. student in Lubbock. And so he is looking not only at the effect of that termination on the cover crop, but also trying to develop models using UAS as well as satellite imagery to better estimate cotton or cover crop termination timing, and developing a tool that producers can use in the region using satellite imagery to estimate when they should terminate their cover crops with weather models. It's way above my head, but I help with the soil water part. So this is just basic experimental design. The only reason I want to show you this is just to show that this is replicated across different, not only irrigation termination timings, but also throughout the plots as well. And so this is what the 8 week, the termination timing at 8 weeks prior to cotton planting looks like. So this is the day that we terminated, and then 6 weeks, 4 weeks, and 2 weeks before we planted that cotton. Typically, we get much better cover crop growth in these systems. We don't irrigate our cover crops, so this is rain fed. We only received about 1/4 of an inch of precipitation throughout the entire growing season, the cover crop growing season. So you can imagine that this cover crop is supplementing itself off stored soil moisture from the previous cotton crop, and we're going to see that in some of the soil water results. So this is just some drone imagery of what those plots look like. You can tell that I'm not very good with a backpack sprayer because I'm not really getting all of the areas that I need to. Especially some of these other plots that you'll see here in a second. But we're just fast forwarding through time through each of those termination timings. And then finally, this is the cover crop that was left final, like we planted into it green. And so this was this is at peak bloom for cotton yield. So you can just see kind of the stand counts and the size of the plants as well in that system. All right, so getting into the data, we're looking at cover crop termination timing. So this is 8 weeks termination. So 8 weeks prior to cotton planting. And he described this as the pre-boot stage for that rye. And so what you can see, these are the plots that we terminated. This is the amount of soil moisture that was in the system when we terminated that cover crop, okay? And so just think about this. This is, so we terminated here, and these are his soil moisture readings up until that point. So it recovered soil moisture about 4 weeks before cotton planting, and that's where we received our first rain. So mid-April, we received about a 1/2 inch rain, and that's showing the system recovering some of that soil moisture following termination. At 6 weeks, similar system, right here are the plots we terminated. We started to see head emergence. We let this cover crop go way too far than we would normally recommend. And this is where, at termination, this is what the rest of the season looked like. So you can notice we're depleting the soil moisture at the surface to a pretty extreme level, but it did recover later in the season, although you're kind of pushing it when it comes to your cotton planting time. At 4 weeks, similar story. Here are the plots. Here's soil moisture at those same depths. So you can see while we didn't deplete as much water because we received those rains at about 6 weeks, we did start to increase soil water right before planting. And then finally, at 2 weeks, notice that we did not recover that soil moisture prior to planting this cotton crop. And we had pretty poor stands in our 2-week stage, and this was also at a dough stage. So just note that your termination time does matter, and it is going to impact your subsequent crop, which is pretty intuitive. And so this is looking at all of them across time, and notice when we see those recovery periods, but this is where you didn't have a cover crop, okay? And so it's important to note that we did store a considerable amount more moisture in this no cover control compared back to that the other cover systems. And so, you know, for us, the benefit for a cover crop is not really to shade the soil or increase soil moisture retention. For us, it's more about controlling wind erosion. And so I will note that we had to sand fight this no cover control system 3 more times than we did. We did have to sand fight even in these other systems, but just note that we had to sand fight more in the no-tills or the no cover system than we did in the others. All right. So I talked pretty fast, so I apologize for that. So we can go with plenty of questions if you want. So in summary, soil moisture is reduced by cover crops, but it can be rapidly replenished with timely irrigation or rainfall. For us, we don't really have the irrigation capacity to pre-water much, so we're relying on our preseason soil moisture as well as those timely rainfall events. Water use following a cover crop follows those four distinct trends where we lose water, we gain water, we maintain water, and then we're going to gain quite a bit of that soil moisture prior to our cover crop planting. The cotton wheat fallow rotations increased our soil water storage and our yield compared back to continuous cotton, either with a cover crop or without a cover crop. And then terminating at 6 to 8 weeks prior to ideal cotton planting resulted in greater water at planting. And so I will note that, you know, this cotton wheat fallow system isn't going to work for everyone. Where we are in Dawson County, we've started a pilot program with the county itself. And so Dawson County is doing a delayed, how would you say it? A delayed tax payment program for a pilot group of producers to where they only pay property taxes on their fields that they're doing this pilot study in on the cotton year, which is their income year. So essentially what the county is trying to do is understand, while they may not incentivize through a tax rebate program for implementing a cover crop, they're delaying their tax payments to a point when producers are making money in a 3-year rotation. It's proving to be somewhat successful. The county is worried about their bottom line budgets for their road improvement programs, but we're seeing it as a really good opportunity, as a carrot for our producers, at least in this one very specific county. So with that, I say thank you, happy to go back over anything and answer any questions you might have. Yep, any questions? Yes, sir. Yeah, so the question, yeah. Yep, so my summary of the question will be, are you using predictive climate forecasts to estimate or changing the cover crop termination date relative to what we did in this experiment? Is that fair? And so, you know, the way that the study is designed is it doesn't really build into that. We're hoping to use that as a covariate for us to analyze the data, but our producers do use that as an estimate. And so tomorrow I'm going to share some data on cover crop adoption in the region. We're only at about 7.5% for the Southern High Plains of cover crop adoption. And most of that is because of NRCS funding is limited by county. But I will say that most of our producers who are using a cover crop are using NRCS funding to do that. So they are limited by that 8-week deadline to terminate, but they will use the weather forecast as an estimate of maybe I could do it 7 days earlier, or I should delay it by 3 or 4 days. And so with this study, that is the ultimate goal, is to utilize weather models to build into our termination models. So we're modeling the cover crop growth itself, so we know how that crop responds to both temperature and water, as well as nutrient availability. And so then to build in predictive climate models to help them estimate, well, maybe you can get the same benefit at 9 weeks as you do at terminating at 8 weeks or 10 weeks out. So trying to build those things in, but in this system, with the 1 year of data we have, we can't do that yet. Is that fair? Other questions? Yes, sir. So the question is, if NRCS funding for cover crop support runs out, how many producers in our region do we think will maintain their cover crops? So I think we can use CRP funding as a good analogy for predicting what will happen. So about 3 or 4 years ago, they changed the rules for CRP funding on the High Plains. High Plains have historically received, majority of CRP funding in the country, and they cut the number of contracts in half. And we saw 50-year-old CRP, and it wasn't called CRP then, but the prior CRP program, we saw about 80% of those who were not going to get CRP funding plow under their CRP and go back into row crop production. Now remember, CRP in our area is like our sand dunes. And so people are plowing in areas that probably never should have been plowed in the first place in the 40s, in the 30s, and we're converting that back into crop production. We had some of the worst dust storms ever in 2018 since they implemented the CRP program in the 1960s. And so the government came back the next year and said, whoa, we'll pay you to put it back into CRP production. So my crystal ball forecast would be that if the federal government stops subsidizing cover crop adoption on the High Plains, we would have maybe 3 or 4 producers per county who have been doing this from a long time. I would say are more progressive producers that would still maintain it. But when we survey our producers, about 80 to 85% of them say the only reason they implement a cover crop is because the government pays them to do it. So I expect we'll see most of them abandon it. Yeah. Yes, sir. Great question. So did I see cattle driving over here grazing cover crops? I saw a little bit. I would say for us, where we had abandoned cotton acres, and we're at about 68% abandonment on the southern High Plains this year for cotton production, we saw some early planted wheat and rye and oats, and I did see a few places that were grazing cattle. I think one of the major limitations, especially farther south, so Plainview is kind of our dividing line between the clays and the sandy loams. South of Plainview, I didn't see any. I saw wheat growing, but I didn't see any cattle grazing. North of Plainview, I saw a few places, but I think it's like an infrastructure question. We're not seeing a lot of people putting up the electric fences or anything else to really graze those cattle. And so I think we need to address the infrastructure question for that. So Dr. Arnall and Dr. Sharma, as well as myself, and Dr. Lofton, we're all on a project to look at regenerative grazing practices in West Texas and Western Oklahoma. And so we're hoping to bring some more of that data to the region. It was a $10 million funded program to evaluate just that here in the area. And so we've seen moderate adoption, but we've had 2 really dry years, and it's hard to convince people to implement a new practice when you've had 2 back-to-back hard years. Any other questions? I'll be around today, and then I'll be here through lunch tomorrow. Yes, sir. Sorry. Great question. Is it profitable? And you talk about the cover crop systems? Yep. Yes. So is it profitable? Great question, and I appreciate that. So it is. You don't lose money by implementing these no-till systems. And one of the things that we see when we survey our producers who are doing this is they're talking about just windshield time. So while you spend less money on diesel, you're spending more money on some of your other inputs, and the loss of yield pretty much balances all of our system out. There's no significant difference in the economic return from a no-till system and a conventionally tilled system in Lamesa. But what our producers who we surveyed about this said is they appreciate getting to go to their kids' baseball games in the summertime when they're not out sand fighting or something else. And so I think there's a little bit of something that we can't compute with our current economic models that just look at income. But you are not losing more money with these systems. You're kind of maintaining the status quo. So, and I will show that data tomorrow. So I should have probably combined both of my presentations at one time and just sped through both of them. But tomorrow I'll talk about the economics of it. And so I'll preface this by saying we don't think it's a water issue that's affecting yield. We think it's a nitrogen issue that's affecting yield. And when we balance for nitrogen, we increase our economic return by about 56% in these systems. So you actually see an increase in gross revenue with those systems. But that's a preview for tomorrow's presentation. Any other questions? All right, I appreciate it. Thanks, everyone.
I'll be the next speaker. I'll introduce myself. So I'm Sumit Sharma. I'm assistant professor. I work in irrigation management and row crops. Most of my work has been concentrated in western Oklahoma. I was in Panhandle for 6.5 years and moved here on campus 5 months ago. So I sit here in Stillwater now. I'll be talking about the irrigation frequency, pushing time or depth. All right, sorry. All right, so I'll be talking about specifically. I'll be talking about the depth of irrigation. Jonathan touched that topic a little bit in his presentation, and I'll be going over like why depth is important and what kind of processes are there that determines that we should be going deep with our irrigation or we should be shallow with our irrigation application. So the first slide is just very regular slide that why do we need to water crops? It regulates canopy temperature. It's a medium through which crops absorb some of the dissolved nutrients. And it actually, the oxygen that we breathe that comes through photosynthesis is coming from water. Water is broken down during photosynthesis process. A good irrigation program, Jonathan highlighted all the points about it, that when and how much we can delay the irrigation, but it's also how can we avoid the losses, that is runoff or canopy interception, avoid water stress, encourage root growth to the deeper layers, or that also we want to recharge our soil profile. And before that water is going to hit the ground, get into the soil, that water droplet is going to get blown away by the wind. It's going to get intercepted by the canopy. It is going to evaporate from the soil surface. And of course, if it gets into the root zone of the plant, it's going to get transpired. For the most effective use of water, it has to go through the roots of the plants into the canopy. Like he used the analogy, do you want to drink the water or you want to pour water on yourself? So the best use of water is when it is absorbed through the roots. All right. It stopped working. Oh. There you go. So I will go through some of the experiments and some of the data that shows that why deep and why not shallow, and somewhere why shallow and not deep. The first experiment is that we did this experiment in corn and sorghum in the Panhandle in a subsurface drip irrigation system where we installed sensors at 6 inches depth just below the crop row, 6 inches depth just above the tape, which the tape was installed at 12 inches, and a sensor that was between that tape. Does this thing work? Oh, yeah, it works. A sensor just between the tape and a row at 24 inches depth. What we wanted to see was that we were going to give water through this tape every day, or we were going to give water to this crop after a few days and see if the crop tries to reach that 24-inch layer to extract water. Prior to this study, they noticed that when they were giving water every day, crop was not utilizing any of that water that was available in the deeper layers. So we did this experiment and we had these 5 treatments. We were giving full water every day to the crop. We were giving full water every 3rd day. We were giving full water every 4th day. And we were giving full water, limited water, that is like 80% of full water every 4th day, and about 80% of everyday crops water demand every day. So what I want you guys to focus on is the treatment 4 and treatment 3, where we were giving larger irrigation events, the deeper layer of irrigation, less frequently on the 4th days. So the green one is limited. So this graph shows metric potential, and this is the sensor at 24-inch depth at over time of the crop growth. So once the crop started putting on biomass, the one which was limited, but we were giving after a few days, less frequently, it started reaching the deeper layer of the soil. So the negative means that the drier it is. So the soil in 24 inches started getting drier, followed by, which was getting full water on 4th day, it started reaching that soil for water later on because it didn't have to early on, it was getting a little bit more water. But when we were giving water every day, whether it's limited or full, that crop was not making effort to reach bottom layers. So, and the reason I'm saying this, last year when 2022 happened and people were irrigating their crops, they were looking at the crop's condition. They were looking at it's 105 degrees Fahrenheit outside, and the crops are curling, and they were rotating their pivots on 24-hour rotation just to get that 1/4 inch water on the crop. It will get the crop wet. That water is going to evaporate, and it's going to take some heat with it, and it's going to make your crop look good for a little bit, but it was not going to help it. So that depth was very important. Moisture sensors that Jonathan talked about can help us, because those moisture sensors we installed for this study are research-grade moisture sensors. This is commercial moisture sensor that we are installing. This was 2021. We received a lot of rainfall early in. We didn't initiate irrigation. Because we had rainfall, we did not put 1 1/4 inch. We put like 3/4 of an inch when we started irrigation. We continued doing that. We came up the second time, and the third time we were going down. This is the profile moisture, the 4 feet profile. My moisture content in the whole profile on the third time was declining. And when we saw it, we slowed down our pivot and brought back our profile moisture up again. How much we put? I think we put that time we put 1 1/2 inches there. We continued, came back to 1 1/4 inch. We continued doing that. The pivot stuck over here. We had a gap. Pivot stuck again after this irrigation event. We had a gap. We started again. We kept it at 5-day rotation. The crop at this point is maturing. It's senescing. Its crop water demand is going down. But the depth we are giving it, applying to it, it's increasing my recharge of my profile. And at one point when I'm looking at it, all right, it's going up and up and up and it's not doing anything, we shut down our water, let the crop suck out everything that was available over there. So the depth we adjusted over here helped us with our crop, and also how moisture sensor helped us in determining, all right, where to increase the depth or where to stop my water. The same happened in this farmer's field. He was giving on daily rotation, putting only 1/4 inch of moisture, and every time he was giving that water, that crop was going down. And the reason is, now I was saying that earlier I said that you put deeper water, the crop will go down. Here I'm saying that he's putting smaller water and profile moisture is going down. And the reason that is because it had profile moisture in it. And I will show you why it was going down, and its roots will follow. There is one more graph before I will show you that. The reason for that is roots will follow what we will ask it to follow. So this was the tape, and it was subsurface drip irrigation. It was this is the tape over here, and a student from Jason Warren took this root biomass data. They took the samples, and the greener part is the thickest roots. And this is the tape. Red part is less thick, and then this is the least thickness of the roots in the soil zone. What's happening is the roots are following the tape because that's where the water is coming. This is over here. This crop was planted at 20 and 40 inches. So this was planted at 30-inch spacing. So this is the tape, and the crop row is 30-inch, and then another 30-inch. There is another crop row, and then 30-inch. There is a tape. This one is 20 and 40 because so one crop row is 20-inch close to the tape, and the other is 40 inches away from the tape on this side. I should have created a plot over here. But because this row was closer to this tape, the density of these roots were getting closer and closer to the tape where the water was. I don't want to confuse you guys, but in my first experiment, I said I increased the depth of the irrigation, and then crops went down. And in the second ones, I said when we were decreasing the depth of the irrigation, the crop was going, the profile moisture was going down. The reason for that is, I have a soil profile that is full. I am applying water to the soil and it's getting wet. And I'm giving water to it every day. At one point, that soil is going to stay wet. And when it stays wet, the infiltration capacity is going to go down. And at that point, the crop is going to go and get water from somewhere. And if there is water in the profile in the deeper layer, it's going to go down there. So when I'm going to for the deeper layers, what I'm looking for, how deep I can go, it depends upon the infiltration rate. It depends upon the moisture capacity of the soil that it can hold, and that depends upon texture. It depends upon the well capacity, how much water I can put, the slope I have, the equipment capabilities, and crop's water demand. Let's see. Here I will explain what I showed you earlier. The infiltration rate of soil varies. The rate is maximum when soil is dry. As the soil starts getting wet, it already has moisture, and its capacity of holding more and more moisture or pulling in declines until it becomes saturated and constant. That's saturated conductivity. And the saturated conductivity varies for different soils. Maximum for loamy sands, and it declines as you go to clay soils. And the plant available water is the opposite. The plant available water is minimum in the sands and maximum as you get into the clay soils. There is one anomaly here, that is the loams, which have better plant available water. Now when I'm 90% of our systems are center pivot. Where do I put my maximum water? I put my maximum water in the outer spans. Why? Because that nozzle in the 8th span of that pivot is going to cover maximum area in the field. So the rate of application should be highest over there. And the inner span has the minimum rate of application. So ponding or runoff chances are highest over here because I'm putting more water over there. I'm putting water at higher rate over there. Now, if I look at the nozzle position and ponding, so before I go there, the nozzle, if it's spray, the water is going to come down and it's going to throw it out. How far it throws is nozzle's wetted radius. And for a 10 feet wetted radius, and I have 5 different soils here, from loamy sands to clay loam, and this is the nozzle distance from the center of the pivot, and this is the time of ponding. For sand, the time of ponding is, a clay loam for the time of ponding is the lowest, because its infiltration capacity is the lowest, as we saw in the previous graph. For the sand, it will take anything that we will give it. But as you go outside in the nozzle, outside span, the 1,300 feet, the nozzle over there that's putting water at higher application rate, that timing for ponding is the highest. Now, where does that bring me? I am going to give water to this soil every day at 1/4 inch, every 2 days at 1/2 inch, and every 3 days 3/4 inch. And I have a moist soil and I have a dry soil. I believe moist soil was field capacity and dry is at permanent wilting point. And if we look at the time for it to pond, it's highest for dry soil because it's not going to pond easily. It's going to absorb whatever it gets, followed by the moist soil. It is going to pond early because it has moisture already. And if you look at the ponding time, I'm giving every day its 1/4 inch right here, that soil is going to pond quicker. I am giving it less water, but it's going to pond quicker. If I increase it to 1/2 inch, the ponding time goes up. So it is not going to pond, or the runoff will start a little bit late. And 3/4 inch is even higher. What's happening is, like I said, I'm giving water every day. Every day I'm giving 1/4 inch, and that water stays on the surface. Before something happens, I'm bringing another round in 24 hours. I'm bringing another round in 24 hours. There comes a point the surface is going to stay wet. When it is wet, and we saw the infiltration graph, the conductivity declines. When the conductivity declines, the water penetration into the soil declines. And when the water penetration into the soil declines, its crop's going to look good early on, but it's using its reserves that are in the soil, and overall profile is declining. I have a photograph that I can show you, but when I'm doing 3 days, I apply that 3/4 inch today, and I come on 4th day and I apply another 3/4. Those 2 days in between, soil had time to rest and a little bit dry. And that dry surface can take has better infiltration than a moist surface. Very rare I see some people giving 3/4 inch. Mostly I see 1 inch or 1.5 inch. So it usually gives more than 3 days for soil to take rest and make that space to get another round of moisture in it. These 3 are a little bit difficult to look. So in the next slide, I actually maximize them or zoom them. So the loam for dry, moist, or 1/4 inch every day, give it a rest, and give 1/2 inch every other day and every 3rd day. I give 3/4 inch, the time of ponding or time of runoff keeps on going up. So it's prudent to give water at higher depths, not at lower depths, because if you keep doing that like we were doing in 2022 to make our crops look good, they were not actually helping us. The soil looked wet, but the crops were not. Like I said, before the water gets in there, the other thing that can get into with small quantities of water we apply is canopy interception. Before, like I said, the first image, the first thing that the water is going to hit is the canopy. And if it gets intercepted there, it's of no use just to help my plant for maybe an hour or two. Jonathan presented this data, but I found a study from China that usually whatever water you apply, and they did it in wheat that was fully grown, whatever water you apply, in general, it intercepts 0.1 inch. So if I am applying 1/4 inch, 0.1 inch out of it, that's like half of that water was intercepted by canopy and never reached it. And if I'm applying 1 1/4 inch, almost 10 or 8% has been intercepted. So the amount of water, when you increase the depth, the amount of water that's reaching into the ground increases. But we can control it if our nozzles are dropped down. If we have LIPA or LISA system that's only 18 inches above the ground, it is actually surpassing most of the canopy, avoiding it. Well capacity. No matter how much well capacity you have, 300, 400, 500, if you want to put 1.5 inches, you can put 1.5 inches. The only issue is the interval between those 1.5 inches will be longer. And if that happens, we will incur yield losses. This is for corn. At points, corn can take as much as 1/2 inch of water in high plains regions per day. So if I am applying 300 gallons per minute, it's going to take me 10 days to come back to put 1 1/4 inch. So on average, I'm applying 3.2 millimeters. I converted into millimeters because this graph was in millimeter per day. But at 600 gallons per minute, I can apply almost 1/4 inch, which is about 7 millimeters. So crop choice should be one. The one that should govern what kind of practice you are going to do for the given well capacity you have. So you can apply as deep as you want to, but you will be limited by the rotations or frequency. Pre-season and in-season irrigation, when you have limited well capacity, this is where pre-season irrigation comes, which I said, the storage in the profile. You want to store that water in the profile before you start planting. And usually it's in April and March or April. Even for those, you want to increase your depth. You don't want to do 1/4 inch or 1/2 inch, because that's windy time for us in the high plains region, and evaporative losses will be very high before the droplet hits the ground. And nozzles can also help. There are nozzles out there which can help with the droplet size. Bigger the droplet, less potential for it getting evaporated. In-season irrigation in these kind of conditions will only help you to meet the crop water demand. So what does that mean? That the profile, and then you are giving it full depth, but the supplemental is coming from the profile that you don't want to lose, you want to keep it. So if you increase the frequency of the rotation or, by reducing the amount of application or the depth, you're losing profile quickly. and you want to preserve it. So early in the season, when crop doesn't have that water demand, you can still build that capacity of your soil storage. And it will work best in deep soils, and roots do not grow in dry soils. One of the reasons I said, if you do not have profile in the soil that is dry, so you have 1 foot of profile that has water, and then beyond that it's dry, your roots are not going to go down. So that's another catch. If you want roots to go down, you have to have profile in the built up. Is depth the only answer? I actually went to this field. This was in Beaver County. The way this field was, it was flat, and then it dipped, and then it became flat again. They were applying 1 inch every time they were rotating. That 20% slope, the water was flowing down through the track, and it was eroding those tracks. They were getting deeper and deeper and deeper, and their pivots were getting stuck. So at this point, you are putting 1 inch, but the slope is so high, soil was not absorbing it. In these kind of conditions, you can speed up because your water is not doing you any good, actually doing you more harm. All that water was getting accumulated in the valley underneath, and that crop looked really good over there because the water didn't even flow, it took the soil and the nutrients with it. Shallow soils. If your soil is shallow, say it's only 1 foot, and it can only hold 1 inch or 1¼ inch, or say even ½ an inch, then you probably don't want to go beyond ½ an inch. Because if you have reached that ½ an inch and your soil's already saturated, anything above that is going to start running off. In those kind of cases, you have to adjust your depth. Sandy soils usually get to be irrigated more frequently because they have low holding capacity, they absorb very quickly, and they do not very good soils in comparison to loams. And slopes I already mentioned, but this over here was about beyond my knee height, it was about my thigh, how deep it went. And that over there was where the motor was dragging. So take home, shallow and more frequent irrigation events. Your soil is going to get wet if you do it more frequently, and eventually you will not recharge your soil profile, and crop is going to use whatever it has in the reserve. And deeper irrigation events usually help with the recharge of the soil, as long as we have our infiltration capacity in mind and water holding capacity of soil in mind. Of course, texture, soil depth and slope, everybody knows their field. Please keep that in mind. And then canopy interception will occur no matter what. You're putting high or low. It just depends on how much deep you're giving, how deep you're applying your water, and that will determine how much it's reaching to the soil. Sensors can help, and that's one of the areas where sensors can help, where they can help us determine whether we're going to increase the speed or whether we need to slow down our pivots. This actually, I took this photograph. This corn, there we go. This corn over here, we were giving ½ an inch every day, but the soil is wet, the corn is still dying. We were giving it water, and it was still dying, and the reason was because it stayed wet and stayed on the surface, and it used everything it had at the bottom to stay alive. That's it. Any questions?